previous speaker mentioned, there are a lot of discussions still even about simplest aspects in terms of connectivity as it is for Kandau, which is nice and which makes the field very healthy. So I will be presenting a different viewpoint. So, and I will be talking actually mostly not about confined superconductors. And I will try to argue that I will present my arguments for your considerations that type 1, type 2 dichotomy is not sufficient for classification of superconductors, and I think I will I have certain systems where I can show precisely that it's not sufficient. Alright, so everyone knows here type 1, type 2. I will just skip this slide, and I will come to simplest Ginsburg-Kandau function of two-band systems. Sorry about this, to just ignore this. And okay, so this is this function was shown several times already. So here we have two complex fields and attributed to Cooper pairs formed in two bands, and then there is interband coupling, which breaks U1 cross U1 symmetry of this function explicitly down to U1. And that means there is only tau parameter. However, our different viewpoints with previous speaker was that from our point, Ginsburg-Kandau theory is an example of a classical field theory, which does not necessarily, the components are not necessarily arising from different broken symmetries. So, for example, if you take, for example, maybe better known high-energy physics examples, you can have multi-component Ginsburg-Kandau expansions where symmetries are broken explicitly, like Nambu-Yon-Lazinium models is just an example which is known for half-wave decay. So essentially, this functional, it doesn't appear, it cannot appear through expansion of single parameter tau. But I will comment a little bit more about it, that you can formally justify this form of classical field theory just as expansion in several small parameters, small gaps and small gradients. But let me simplify it further, and let me start discussing, as I start presenting my argument in connection with U1 cross U1 theory. So we don't consider now two-band superconductors. There are plenty of examples known for decays where you have systems with symmetry, broken symmetry, just U1 cross U1, have a mixture of independently conserved condensates. So I will not list all the examples, but let me just give you most apparent example. Superconducting states discussed in connection with liquid metallic hydrogen, or protonic Cooper pairs forming together with sigma minus gyperonic Cooper pairs in the neutral star. So then you can have several condensates which are coupled by vector potential. And if you ask now the question whether or not you can classify this theory by Ginsburg-Kandau parameter, the answer is apparently not, because simply you have several coherence lengths attributed to different condensates, and magnetic field penetration X, you have three parameters. You cannot form a single Ginsburg-Kandau parameter couple. And if you now look at vortex solutions in the systems, then because of coupling by vector potential in two components, which is always present, we'll make vortices form bound states. So these are two these are the density of modulus psi1, modulus psi2. We have a pair of vortices, and their cores of both condensates, they are concentrated because of electromagnetic interaction. If you would like a detailed calculation why they should be always concentrated, for example, you can see it in this paper. And now, if we write, if you take the most simple example and write the most simple coherence length in the system, then if you, in general, in E1 cross E1 systems, one has different critical temperatures for different components, and at the lower critical temperature, Landau's theory dictates us coherence length. One coherence length should diverge, while magnetic field penetration lengths should be finite. Then, unavoidable, if you have U1 cross U1 broken symmetry, unavoidable, first of all, you cannot have single Gisbert-Landau argument, and also generically, quite generically, near phase transitions from U1 cross U1 to U1 phase, you will fall into the either type 1 region, or the region where one coherence length is smaller than magnetic field penetration length, so another is larger. And this is the region of our interest. You have systems with several coherence lengths, one coherence length smaller and another larger than lambda. So this is what was termed like 1.5 superconductivity, something which can be expressed in 3 symbols. So essentially, then one of the, not state defining, but one of the consequences is the following. So we have now vortices, so this is pair vortices. And then if you look at a single vortex, it will have 2 cores. One core will be much larger than lambda, and another much smaller. And if you consider interaction between these vortices, so it brings them together, first they start feeling each other by the larger cores, but will not feel each other by each other's magnetic fields. So the interaction will be core interaction will be attractive. And then when they get close together, they feel magnetic field of each other, and the interaction is repulsive in that case. And let me hope that it works. Let me try to show you numerical simulation. So we take this numerical simulation of we have this picture. We start with the initial configuration of 9 vortices. This shows magnetic field. Core of one component is this type. So this component with smaller core. Cores of the second component with larger cores. Current density in first component, current density in second component. This is just initial configuration. If we start minimizing the energy, vortices start attracting each other, and at the end of the day, the ground state is that you get vortex cluster. So you have one component forms vortices, so this one component has vortex currents, and the second component is relegated almost all the current to the boundary. And in that particular example of big disparity of coherence lengths, you have a coexistence of type 1 and type 2 behavior. So you have vortex cluster, one component has current preferably circulating on the boundary of the vortex cluster, similarly like surface current around type 1 domains, but instead of type 1 domain, we have inside it vortex cluster. So now this is just a snapshot of this current in one component and current in the second component from numerical simulations. Okay, and then let me now, this was U1 cross U1 series was not applicable to 2-band superconductors. Let me tell you how now we can take into account interband interaction. Okay. So we take U1 cross U1 Gisbert-Landau energy functional, and we add interband Josephson coupling. Okay, like if you, this is, we will just do it phenomenologically, but if you want very, very formal justification of derivation of this Ginsburg-Landau functions, there was a paper 2012, this ILC Live. Okay, but now, so what happens if we add interband interaction? What happens with coherence links? And okay, first let me just say that if we denote by U ground state density of the condensate, then very little happens if we add interband interaction, because the density of the ground state density of the condensate go up. The inverse magnetic field penetration length, which we denote by mu A, mass of the gauge field, it goes down. But with coherence length, it is more subtle. So if you have, so our point is that if you have any non-zero interband coupling, one can no longer attribute coherence length to a band. So if you calculate, for example, one-dimensional problems of asymptotic behavior of the fields, so delta fields, then for any non-zero interband coupling at any temperature, both bands will have the same long-range asymptotics. So, but at the same time, both bands will have another contribution to the asymptotical behavior with a different coherence lengths. So formally that means if you have one-dimensional problem of condensate recovering the ground state density, the solution can be parameterized in this form. It can be represented as two Bessel functions for each of the fields. And then one can introduce some parameter theta, which is called typically mixing angle in many contexts. And then, okay, if both deltas and both psi's have long range are dominated by one of the coherence links. Mu2 is just 1 over psi 2. Mu is just inverse coherence links. Then K1 is there is only one coherence link. In two-band system, actually no, because we can always go to linear combination of the fields, each of which has unique exponential localization. So formally, it is just two-component generalization of exactly the same argument which we find in single-component case in Tinkham book. Okay, to speak about asymptotical field, just first linearized Ginsburg-Landau theory around the ground state, high are small directions, and then you can always diagonalize linear theory into two decoupled Klein-Gordon equations, and therefore that means that in two-band systems, coherence lengths are not associated with gaps in different bands, but are associated with linear combinations of gaps in different bands. So when one diagonalizes, one just go to the test. There is a hybrid, what we call hybridization of coherence lengths. And if, and then we can calculate, interband corrections to this coherence lengths, this mixing angle, etc. And then exactly the same procedure can be done, it has been done for any kind of interband coupling, for any kind of most general Ginsburg-Landau expansions. And the answer is that unless interaction is sufficiently strong, interband interaction does not eliminate type 1.5 behavior. But what is dramatically changed is that coherence lengths are not associated now to individual components, but it's associated with the linear combination of the bands. And so I will just flash a little bit what happens in microscopic interactions, but I will not talk about it. So we have inverse coherence lengths in U1 cross U1 theories, calculations from Eilenberger equations, but let me just flash it. Okay, we have V1 cross V1. We have two different TCs. Then coherence length diverges at the point where symmetry is broken. We have one coherence length divergent to one TC, another coherence length divergent to the other TC. And if we plot coherence lengths in the normal state, fluctuation regions, it will start growing again. Now, if we add any non-zero interband coupling, then we eliminate phase transition at this lower TC because it's singular perturbation explicitly breaking symmetry. But if this perturbation is small, we still have a maximum of coherence lengths, and then we get avoided crossing, and then at TC only one coherence length can diverge, and second coherence length should stay finite to be in agreement with Landau theory of the phase transitions. And again, here coherence lengths are not attributed to different bands, but they are attributed to different linear combinations of the bands. And if we increase some mixing angles, the two mixing angles, and if you go to macroscopic theory, if we increase coupling further, then the avoided crossing grows, and at sufficiently strong coupling, one coherence length disappears. And then there was already flashed, so there was a discussion of Viktor Mashelkov experiment, who coined this term type 1.5 sphere conductivity, and started this field by observing vortex cluster. And I will be talking about different material. Three bands superconductors, strontium rutinate. For a long time there were some hints, of vortex clusters by three groups. Vortex cluster formation in this multi-band material. Of course, natural interpretation is just spinning. So the first interpretation, I think now there was a very good experimental evidence published that it is not pinning vortex clustering in this multi-band material. So this is the recent paper they obtained. So this was interpreted as that its material falls into type 1.5 plus, and there was obtained the following phase diagram with vortex clustering. Again, by itself, vortex clustering should be by default attributed to pinning. But however, this experiment shows that it's something which I cannot make consistent with pinning. So this is a muon scattering experiment which can tell what is the fraction of the sample which contains vortices and what is the magnetic field, what is the magnetic field strength in these regions. And essentially, this very experienced experimentalists say that they observed something which they never seen before. First of all, so if we cool down, then red curve is the fraction of the sample containing vortices. So suddenly the system phase separates in the bulk very strongly in vortex clusters and flux-free Meissner states. So there is the existence of the Meissner domain in vortex clusters. Okay, can be said spinning, but what happens at very low fields when in a single component we would have no temperature dependence of penetration lengths and coherence lengths to a substantial extent. Suddenly, in these vortex clusters, the magnetic field, the strengths, start dramatically growing. So if you go quite far below DC, suddenly this vortex cluster start rapidly contracting, field growing several times. So that essentially tells us that there is there is attracting force operating at very, very low temperature, which contracts these forces, very big rise of magnetic field. And this is exactly consistent with microscopic calculation into band theory, where we, instead of having divergent coherence lengths, we break symmetry explicitly, we get a maximum. So this is inverse coherence length. And then if we cool down, so then here we will get that coherence length growing when we approach this point. And if we calculate intervortex interaction energy, so this is high temperature, lower, and then suddenly at low temperatures we fall into the region where one coherence length is larger than penetration length, and another is smaller. And then vortex clusters forms, and it should they should contract as a function of decreasing temperature. So, and let me think I'm running out of time. Let me just very briefly comment on S plus IS superconductors, which are now advocated for iron-based superconductors. Let me tell you that in that case we can we will just maybe flash the results. So do you have 1 minute to 1 minute? So essentially this is phase diagram for this superconductor by Maiti and Chubakov, and so on. So here we have U1 broken symmetry. Here we have the cyclic of U1 broken symmetry, and here we have S plus IS state, which breaks U1 cross Z2. So going through this phase transitions, we break extra symmetry, and we have divergent coherence lengths, and this was analyzed in this our paper with Karlstrom and Julien Darrow. That there is very peculiar effect in S-plus superconductors. The coherence lengths they are mixed not only between different bands, but they are also mixed with legged modes. So there is no legged modes. Instead, there are 5 coherence lengths mixing density and phase difference modes. And for this reason, at the phase transition to state with broken time reversal symmetry, sorry for flashing this loss without any explanation, let me just say the message. So there is peculiar new effect, elimination of legged mode and appearance of new collective mode, and that gives divergent coherence lengths and blow up of vortex cores at the transition to S plus IS state, leading to type 1.5 behavior generically, so by symmetry. And I will just then, sorry for running over the time, I will just stop here with the summary table. What I will do. Thank you.
Time 2 or 3 short questions with short answers. Yes.
To the point, maybe the simplest thing you have shown over in 2-band superconductivity definition of different types, right? You can take the same as Alex Waddle in the beginning and define the boundaries in a temperature area, okay? By defining the line at which vortex action changes sign and the line where Hc equal to Hc2. Okay? So what I'm trying to say is that by your definition of type 1.5, it will be much smaller than this area that you obtain in your model, 2 component. So would you agree that then your definition is incomplete? Should we have 1.3 and 1.6?
So first of all, so our calculations do not give the same phase diagram. So we don't, where type 1.5 is not connected to Bogomolny point. And like our definition for type 1.5 is just very simple in six symbols. One coherence length small, another coherence length larger. So then, having multiple bands does not necessarily imply having multiple coherence lengths. That for sure. And having multi-band Ginsburg-Landau theory, you need to have more conditions to be met. And
again, in microscopic theory, you would define this area. In microscopic theory, you would define this area by vortex attraction on the top, and H equal H2 at the bottom. That's what I'm saying.
It's like in one. So how we define it that even in microscopic theory is also defined it whether or not there exist coherence lengths, two coherence lengths. Yeah. So we don't define it this way as you mentioned. So although you can we define the existence of two coherence lengths and satisfying this. Or maybe I missed your question.
There's still another urgent question.
Yeah,
Short.
very short one. Egor, almost 5 years I try to understand your project. Now I would like to get an honest answer.
Yeah.
You respect Landau theory of phase transition, or you do not? Tell me honestly.
Yeah, of course. As I mentioned.
No, tell me you
yes,
respect or not.
Yes, I respect.
So then, why two other parameters?
It's not order parameter. So that is what it should. It's not order, and it's not even something which is invented by me, but it goes back to decades. So this is multi-component classical field theory. Multi-component classical field theory is not necessarily written for order parameters. So simplest example, Kosterlitz-Tauris transition, there is no order parameters, this is classical field theory.
But how then you constructed the Ginsburg-Landau function?
Yeah, it's called. I call
You call Ginsburg-Landau function, but it's constructed for.
This is a rather
not for order parameters. There are many examples when Ginsburg-Landau function was constructed by not for order parameters.
Okay, this is a quite technical discussion, and we have in 15 minutes time to continue discussion with some coffee. Thank you very much. So now we have a short presentation of our